So we just talked about acid and bases and its fundamental definitions. Now in this section we'll talk about strong and weak acids and bases. Okay? And when we say strong and weak here, it's easy to confuse between low and high concentration. They're a different concept. Okay? So concentration doesn't have to do with the strength of the acid per se. And also, generally, if you have a strong acid, it is also a more dangerous acid, but not all the time. A notable exception is that HF is a weak acid, but it's actually very, very dangerous, very, very toxic. Okay? So let's now go over the definition of a strong acid. So I'll give you an example. If you get this molecule, which is called hydrofluoric acid, and you dissolve it in water, I'm omitting all the states now for clarity. If you dissolve this in water, it dissociates completely into H+, which remember, we write as H3O+, and its other anion iodide, right? So this is a 100% dissociation. Or we say it's a complete dissociation. What does that mean? Dissociate. What does it mean to be 100% completely dissociated? So if we were to draw a graph, the y-axis here is the concentration. If I put things in bracket, that's a note for concentration. And I say initially, I have this much of HI, right? So this is the before. Once I add it into water, what do I have? Let's say if I have 100 molecules of HI, how many molecules of I minus and how many molecules of hydronium will I have? 100 of each, right? So they break up completely, 1-to-1 ratio. I minus and hydronium. Okay, that's what we call a complete dissociation. All of HI becomes I minus and H3O plus. Now, what's a weak? So that was our strong. What's a weak acid? Okay, our prime example for a weak acid, like we just mentioned before, is hydrofluoric acid, HF. When you have HF put into water, okay, remember that water attacks this proton, so it's the base there, so that you get hydronium ion, leaving you fluoride all naked, F minus. It turns out though this reaction isn't very favorable. This F minus isn't very happy being deprived of the hydrogen, so what happens is it attacks back and reacts back with the hydronium. Once it reacts with the hydronium as a base, it's going to take away the hydrogen. If it takes away hydrogen, it becomes HF again and water again. Right? So we have this reversible arrow. So the definition of a weak acid is an incomplete dissociation. Dissociation. That means that in solution, you actually have a lot of HF left and very few ions. So what does this graph look like? If we do the same kind of graph over here, concentration, in the beginning, let's say you have this much of HF. What happens afterwards? It turns out that afterwards, after putting in water, you still have a sizable amount of HF and very few of H plus or H3O plus and very few of F minuses. Right? With this graph, do you see the difference between a strong acid and a weak acid? In a strong acid, your HI completely is gone. There's no more HI. All you have is I minus and hydronium ion. In a weak acid, you have most of your acid left over. Before, after, there's still a lot left, but very few ions associated. And bases is the same way. If you dissociate completely and you get hydroxide ions, you are a strong base. If you dissociate only weakly and then go back to your molecular compound, then you are a weak base. So how do we know something is a weak acid or a strong acid? Well, there's a list. And on this list, there's only 6 acids you need to know that are strong acids. Every other acid is considered a weak acid. Okay, so what are these strong acids? So there's a couple of the halogen one, HI, HBr, HCl. And then there's this funky one, HClO4, which is a polyatomic perchlorate. So this is perchloric acid. And then you have H2SO4. Do you know what this one is? Sulfuric acid. What about HNO3? Nitric acid. These are your 6 strong acids. So know these, and the rest of your acids are weak acids. And in terms of bases, strong base, or basically metal from column 1 and column 2. Anytime you have an ionic compound, for example, NaOH, if they dissociate completely based on the solubility rules, you're going to be a strong acid. Right? So KOH, LiOH, so on and so forth. So check your solubility rule to know if something is a strong base. Again, how do you know if it's a strong base? If it's an ionic compound with a OH as a polyatomic ion and it dissociates completely because it's soluble in water, it's a strong base. If not, then it's a weak base. Let's do a checkpoint. Which of the following is the correct equation for the dissociation of a weak acid in water? Alright, so let's see if any of these answers don't make sense. A, H2SO4, well, off the bat you know it's a strong acid, so that can't be the answer. B and C the same way. HCl, they're strong acids, so they are not the answer. The only answer there is HCN. HCN is not one of the 6 strong acids, so that must be the weak acid. And how does it dissociate in water? Well, water will accept the proton, so become H3O+, leaving you Cn-. Very good.